Hello everyone, welcome back. Today it is going to be the second lecture on matrices and determinants. We've already covered the algebra of matrices and now we continue our journey further. So let me now quickly share my screen with you all in the start the lecture. Okay, so in fact, we had stopped at an example which says that A and B are matrices, then AB equal to BA. So if you remember, we had done that AB equal to BA, AB equal to A plus B, and we had to prove that A and B commute. So we had done with this. And I now want to solve some two matrix equations, which are really important. So two matrix equations. One is x squared equal to I, and the other is x squared equal to 0. And obviously for x n by n, we can't hope to do it. So let's restrict our attention to x 2 by 2. Means we want 2 by 2 matrices such that we will have this kind of thing. Now let me write x. So first we'll do this one and then we will come back to this. So first let me start with x squared. I don't need this one. So x squared equal to I, and x is a 2 by 2 matrix. So I can take x as usual, as x is AB and CD, the 2 by 2 matrix. By now we know how to write x squared quickly. X squared is A squared and plus BC. To remind you that if it is this kind of thing, ABCD, and if you are doing a square, then quickly write first row as A squared and then product of these numbers BC. And second element you can write as B times A plus D, that's trace of A. And similarly here C times A plus D, and this is D squared plus BC. So we write A squared plus BC and B times A plus D, C times A plus D, and this is D squared and plus BC. This number, this expression, we want it to equal I. That is, we want this to be the matrix 1, 0, 0, 1, which leads to a system of equations in A, B, C, and D variables. So A squared plus BC equals 1, B times A plus D, that is trace, equals 0, C times A plus D equals 0, and D squared plus BC equals 1. Now our job is to get the quadruples A, B, C, D, these quadruple satisfying the system of equations, of course, simultaneously. So let's attack the system where it is the weakest. You must have heard that you must try to break the chain where the link is the weakest. So it appears that B A plus D equal to 0 can give us more information. So I'll impose a condition, and so I will start like that. Okay, let's make the case work on A and D. So if A plus D is 0, then this equation, let me number the equations 1, 2, 3, and 4. If A plus D is 0, then 2 and 3 are satisfied, and we don't get any information on B and C. But if A plus D is 0, then 1 and 4 both imply the same thing, because A is minus D, so we'll get A squared plus BC equal to 1. So it means if A plus D is 0, we are getting just this much. Means A, B, C are not completely determined, but they satisfy some relation. We can record that this kind of matrix, that okay, so we got that x equal to, I can take, say, A equal to alpha, and then D will be negative alpha, and then let's say B is some beta, and this is some gamma. So it means we say that these are all solutions such that alpha squared plus beta gamma equal to 1. It means in this case, the solution consists of all the quadruples A, B, C, D such that A and D are equal and negative. So alpha minus alpha, and this is beta and gamma. And alpha, beta, gamma are related by this equation. This is the relation by alpha, beta, gamma. So any matrix X satisfying this condition will be a solution to x square equal to I. Our original equation that I'm scrolling, it is here, x square equal to I. Another class of solution, we have made the case work a plus d is not 0. Another is 0. Other case work is that if a plus d is not 0, if that is not 0, then 2 would imply that b must be 0, and 3 would imply that c must be 0. So we are good. We are getting b and c all 0, and then a square equal to 1 and d square equal to 1. That was your 3 and 4 that give you this kind of thing, a squared. Because a plus d is not 0, so we can take a equal to 1, and then d we cannot take negative 1, so d has to be still 1. So a is 1 and d is 1, and similarly a is negative 1, d is negative 1. So in this case we are getting our solution as the answer says a and d, they are both equal. Of course, because a plus d is not 0, so we will take 1 and 1, and of course b and c are 0, or we have negative 1, negative 1, 0, 0. We quickly identify them with the famous matrix I and negative of I, identity matrix. Combining these two cases, combining this case and this case, we can say that in conclusion, so we'll say in conclusion, x square equal to I, where x is 2 by 2, has solutions of the kind alpha, negative of alpha, and beta and gamma, with alpha square plus beta gamma equal to 1. The numbers have this relation. And other cases is I and negative of I. They two are obvious solutions. I square, of course, equals I, and negative I square also equals I. So that brings us to the solution of this equation, x square equal to I. Let's now get to other thing. X square, we want to solve x square equal to 0. First, some background. There is a concept called nilpotent matrix, although it is not named in JEE syllabus as such. Nilpotent matrix. So if they use it, they will have to define it. So nilpotent matrix, we say that if a n by n is a matrix, if a n by n is a matrix such that a to the power k equal to 0, for some k to the power k is 0, then we will say that A is nilpotent. We will say that A is nilpotent. And we can also define one more term, that if m is the least positive integer, m is the least positive integer such that a to the power m is 0, then m is called the index. M is called the index of the nilpotent matrix. It is called the index of the nilpotent matrix A. That's just for definition. So essentially we are looking for x square equal to 0, means we are looking for a matrix X such that X is nilpotent and of order 2 by 2. So we'll again start with, let's take X equal to AB and CD, AB and CD. And so you will have x squared equals, already we did our work, so we need not do again, a square plus BC. And then this is d square plus BC, diagonal elements. Here you have got b times a plus d and c times a plus d. This time you want them to be equal to not I, but all 0, 0, 0, null matrix. You want them to be null matrix, 0. So everything is nil. So you get a square plus BC is 0. B times a plus d is 0. C times a plus d is 0. And d square plus BC equal 0. Again, let's number. There are 4 equations, 1, 2, 3, and 4. And we want to find all quadruples A, B, C, D that will constitute a solution of this set of equations. So we can continue our work, and let's again focus on A plus D. So if A plus D is not 0, if A plus D is not 0, then you get 2, and 2 implies B equal to 0. 4 implies C equal to 0, because that's the only way now 2 and 3 can hold. So they imply B and C 0. Then when you come to n1 and 4, and then 1 implies, because now b is 0, so 1 implies a square is 0, and 4 implies d square is 0. Of course, that gives a0 d0, but then a plus d is 0, but we started not 0, so this case is not possible. You run into some inconsistency, it is not possible. So the only possibility is that a plus d has to be 0. And if a plus d is 0, then we can have things, because if a plus d is 0, then we will again start with this one, a square plus bc. So let's write a equal to alpha, d equal to negative alpha, and then a squared alpha square plus bc equal to 0. So we can choose b to be beta, c to be gamma, such that alpha square plus beta gamma equals 0. So we can say that all such matrices solution is given by x is alpha, negative of alpha, this is beta, and this is gamma, such that, or numbers numbers alpha, beta, gamma satisfying, they satisfy alpha square plus beta gamma equals 0. So we have done the solution of two fundamental things, x square is 0, x square equal to I. Let's introduce a new concept now. So we already have done enough of algebra of matrices. So let me define interesting aspect of this one, inverse. So inverse of a square matrix, it is defined for only a square matrix. A square matrix, I may say order n, any matrix, all right. So inverse of a square matrix, if I define, the definition says that let A be a square matrix of order n, that is A is n by n matrix, then a matrix B, if it exists, we don't know it exists or not, if it exists, such that AB equal BA equal to IN rather, we'll call I for brevity. N stands for the order of matrix, which is understood here I. So if AB equals BA equal to I, then so we say that a matrix B, if it exists, such that this is an inverse of, is called an inverse of A. So it means given a matrix A, if you can find a matrix B such that AB equals BA equals I, then B is called an inverse of A. Then this B will be called a inverse of A, an inverse. Note the word an inverse of A. Did not say the inverse, but it will soon turn out, I will prove in a couple of sentences later, that of course this becomes the inverse. We can talk of the. So we'll prove that inverse is unique. So in fact, one theorem says that this is uniqueness theorem. So we say that a matrix possesses invertible inverse. So let A be a matrix, a square matrix. Let A be a matrix which is invertible. Then you have to prove that the inverse is unique. The inverse is unique. For that, we fall back on definition. Normally, uniqueness we define like this, that we say, okay, so let B and C be two inverses. So note the word two inverses of A. What does that mean? That means that by definition, AB equals B equal to I. So A times C, so AC equals CA equals I, because C is the inverse of A, and also B is the inverse. So AB equals BA equal I. So these two are inverses, B and C. Our goal is to show that in fact B equals C. So we started by definition, nothing more. Such a beautiful proof. We are just using definition of the inverse. So to prove that in fact, if an inverse exists, then it must be unique. And so N will imply the, and will give rise to the. So now AC equal to CA. What I do that here AC, I write AC is I play with it, I multiply B. So this is pre-multiplying. So this is BAC equals B. So we get BAC is B. Now, so I pick this one, AC is I. Now I'll pick this one, BA. So we have BA equals I, such a beautiful proof, BA I, multiply by C, and this time post multiplication. So you are doing BAC equal to I times C. So it means you are saying that BAC is nothing but C. Now BAC is C and BAC is B. They together imply that BAC is B is C, and that is equals B equal to C. So we have proved that if the definition allows two inverses of A, then they must be same. Means that inverse is unique. So we can say this is, so you will find in many books that this is called the, but then definition talks of not the, definition is and. So don't be surprised when you see like it. So inverse of A, and then we have proved the inverse, and so we can talk of the unique thing, that the inverse, the inverse. So you have got a name something. Okay. Now, if that is the case, then we can move further and we can derive a condition. So a result says, very important result, that the necessary and sufficient condition, that always gives trouble to student. The necessary and sufficient condition for a square matrix to be invertible, for a square matrix, let's name it A, to be invertible, for a square matrix to be invertible, is that det of A is not 0, or determinant of A, or I can say this symbol looking like modulus. So this is not 0. So we are saying that det of A is not 0. It is the necessary and sufficient condition for a square matrix A to be invertible. So first I prove the condition of necessity, that it is necessary. The condition is necessary. Means that you have to prove that if A is invertible, you have to prove that if A is invertible, means inverse exists, is invertible, implies det of A, determinant of A cannot be 0. That's plain. We have already known by now definition that A is invertible, means A is invertible, means A has an inverse. That means that B times A equal to I, or even it was actually AB equal to BA equal to I. I can take any one part, so BA equal to I, it follows from here. If A is invertible, then BA equal to I, something much more follows. BA is I is enough. Now I can take det on both sides, so determinant of BA, I apply determinant on both sides, determinant of I. Now determinant of product of matrices is product of determinants. So this is det of B times det of A. So there are two numbers, is det of I, that equals 1. And so because numbers alpha beta equal to 1, then alpha is not 0, beta is not 0, nothing can be 0. Otherwise left will be 0, right will be non-zero. So we know from here that det of A is not 0. So if A is invertible, then det of A is not 0. And let's prove the other way around, that is called sufficiency. Means you are saying that if det of A is not 0, if you are given a matrix A, a square matrix, and det of A is not 0, then A is invertible. Then A is invertible. This is a constructive proof. Means we create something suddenly and then we say you that, okay, this is the proof. So construct. So we are constructing, say, a matrix called, say, P, some matrix P, I'm saying. So this P is 1 by determinant of A. This is like this. And adjoint of A, or I can write 1 by det of A, adjoint of A. Adjoint comes in determinant, so adjoint of A. Now, if I multiply P with A, this is PA, then this is 1 by determinant of A, adjoint of A times A, multiplied with A, and then this will be 1 by det of A, and this will be nothing but det of A times I. In fact, we are using a property very important property that A adjoint A multiplied with adjoint Y, A is I, and is also equal to adjoint A multiplied with A. Means A and adjoint A, they commute and they give I. Now, if this is the case, then det of A times I, this det of A comes out because not 0. And this is, we can define this because det of A is not 0. That is your here, det of A is not 0, so you construct. And so det of A comes out, so this becomes just I. So we get PA equal to I. Similarly, we can prove that AP equal to I. Means that we have found a matrix P, we have found some P, we have found a P such that AP equal to PA equal to I, and we know that P is an inverse, P is an inverse, but we know that inverse is unique, so in fact P is the inverse. P is the inverse, so from N we have come to the because we have proved, so P is the inverse. So this proof, although very elementary proof, but it tells you the power of simple stuff, that how to combine them in clever ways. Let's move on to an important say terminology definition that says that non-singular matrices, non-singular, that's just a name, non-singular. So a square matrix A is said to be non-singular. It's said to be non-singular if determinant of A is not 0, and it is singular. It is called to be singular if det of A equals 0. With this terminology, we can express the previous theorem that the necessary and sufficient condition for a square matrix A to be invertible is that det of A is not 0. We can say that a necessary and sufficient condition for a square matrix A to be invertible is that it must be non-singular. It must be non-singular. In terms of that, we can write, if it is non-singular, means it is invertible. So we will use them interchangeably. Non-singularity and invertibility both would mean same thing, because one implies the other and the other implies the one. So next, what we can do is we can prove one very important conclusion from here. That conclusion is this one. Let me change the color maybe. So the one result says that let A and B be two square matrices. Let A and B be two square matrices of order n. If AB equal to I, then BA equal to I. Means what you have to prove is that A and B are two matrices of order n, square matrices, of course, we are doing throughout. So we are saying that if AB equals I, we are saying AB equals I implies BA equals I. Means we can just change. The order can be changed. You know that in general, the product of matrices is not commutative. So it deserves to be a theorem in its own right. And that also tells you that we will make some applications of it while calculating inverse. So this solution I will go like this. AB equal to I. Now AB equal to I can take det on both sides. So I will get det of AB is det of I, that is 1. And so det of A, that's a number, and times det of B, that's another number, is equal 1. So product of two numbers is 1. It means none of them can be 0. So det of A in particular, det of A is not 0. So already we know that det of A is not 0 is both a necessary and sufficient condition for A inverse to exist. A inverse is unique, so I can say that there is something called A inverse. We denote by A inverse, the inverse of A, unique, so I can have this name. So inverse is there of A because det of A is not 0. So now AB equal to I given, I can multiply A inverse throughout. So A inverse pre-multiply A inverse AB is A inverse times I, that is just A inverse. And I can associate A inverse with A. It is associative, the product. So A inverse A is equals I. So I times B is A inverse, and I times B is still B. So B is A inverse. So we got B is A inverse. Of course, that was the name. So B is A inverse. So once B is A inverse, now I can multiply them, post multiply with A. So I'll get BA is A inverse, and A comes to the right. So A inverse A becomes I. So you get BA equals I. So from AB equal to I, we have derived BA equal to I. So we can say that AB equal to I implies BA equal to I. We will use this result in finding inverse and showing that only this much work we need to do, nothing else. Coming to the important result, one very important result is this, that let A and B, so let A and B be two square matrices again. So square matrices of same order, same size, same order, and AB equal to 0 means AB is null matrix. Then the idea is, what can we conclude from it? There are three results. First result says that one of them must be singular. One of them means at least one, at least one, at least one, or some of them. SOE means some, all. That is first. Second says that if A is not 0, then B must be singular. And third, we can combine them. Third says you can combine second only two times. If A is not 0, B is not 0, none of these 0, then both must be singular. Then both must be singular. Means these are product of two matrices. So idea is that that product of two matrices is 0 square matrices, and then you have to prove that at least one of them must be singular. Means it cannot be that both are non-singular. That's not possible. Both are non-singular. And other is that if A is a non-zero matrix, if one of them is non-zero matrix, if one is 0, then of course things are 0. So if one of them is a non-zero matrix, then the other must be singular. And third is that if both of them are non-zero, then both must be singular. So we must always try to put all result in the form of language, because language also have power. So of course it's good that we use math and then language together. Now, so I prove first one first. No, they must be singular. So this is proof by contradiction. First part we will do like this. It is that AB equal to 0 implies one of them must be singular. You say that suppose none of them is singular. Or we can do directly also, that AB equal to 0. Better it this one. We can take data on both sides. So I'll write data of AB is data of 0, that is 0, and data of AB, so determinant of products, is product of determinants. So data of A, data of B equals 0. So that gives you that at least one of these numbers must be 0. So data is 0 or date B is 0. And so hence claim is established that one of them must be singular. Both also can be singular. In math, when we say odd, then odd means that it is inclusive odd, that both scenario can happen. Second, we would do well by doing proof by contradiction. So second is we do proof by contradiction. In that we assume first something. So if A is not 0, then B must be singular. We negate it. We say that no, B is, so let B be non-singular. Assume B is non-singular. Assume B is non-singular. That is data of B is not 0, non-singular. We have to prove it is singular actually. You assume B is not singular. So date B is not 0. That means that B is invertible. B is invertible. So B has an inverse. So B has an or the inverse. So B has an inverse called, say, B inverse. Now let's go back here. AB equals 0. I can post multiply with B inverse. So B inverse is 0 times B inverse, that is 0. And B inverse, of course, I can associate like A times B inverse equal to 0. So that's A times I equal to 0. and so that gives A equal to 0. So you get A equal to 0, but remember, A was non-zero. A was non-zero. So you got a contradiction, and so we can claim that B must be singular. Let me stress this proof. This said that if product of two matrices is 0 and one of them is a non-zero matrix, then the other must be singular. So one of them is non-zero, other must be singular. So we said that, okay, let the other be not singular. That is, we said that let det of B be not 0. Okay, not 0 implies B is invertible. So we have got something to play with. That's B inverse. B inverse, you got a weapon. So B inverse is a potent weapon. Now AB equal to 0. Now post multiply with B inverse on, of course, both sides. So AB multiplied with B inverse post multiplied equals 0 times B inverse, that is 0. And associate, because product is associative, so A BB inverse is 0, AI equals 0, and that equals A, that means A equal to 0. Contradiction, because it was given that A is not 0. So it means if product of two matrices is 0 and one of them is non-zero matrix, then the other must be singular. Third is just combination of those two. Third is nothing. Third is, you are saying this one, that both must be singular. So it's obvious. Suppose you assume that A is not singular. Suppose you assume A is not singular. A is not singular. Then you will get implies B equal to 0, but B is not 0. And if you assume B is not singular, then you get A equal to 0, but given A is not 0. So a product of two matrices, both of them are non-zero, it's 0 matrix, then both must be singular. So in all cases, you are seeing that at least one must be singular. Next, let us apply this problem to a tricky example. So A and B be different square matrices. So it is given to be different. So A and B be different square matrices of same order. Such that A cube equal B cube, means cube are equal, A cube equal B cube. And you also have A square B is B square A. You have to find determinant of A square plus B square. So you have to find this determinant of A square plus B square. It looks quite strange that how B square plus B square will form. There is no rule of det of A plus B. Of course, det of PQ rule is there, det of P times det of Q. Det of P plus Q has no rule, and so we are stuck that what to do. But don't worry, there is some motivation. So we are writing first A cube equal to B cube, and A square B is B square A. This A square plus B square is the hint, and A and B with different square matrices. Now if you subtract, we'll get A cube minus A square B is B cube minus B square A. Be very careful when you take sort of common in the matrices, because you always have to keep in mind whether it is pre-multiplication or post-multiplication. I can write this as A square pre-multiplied to A minus B, or A minus B post-multiplied to A square. Either way, A square A minus B, and here you have got B square and B minus A. That's by 1 and 2 given. We subtracted 1, 2, and we arrived at this result, A minus B. So now I can write A square A minus B and negative of B square B minus A equal to 0. So I can write A square A minus B plus B square A minus B equal to 0. That means that I can write A square plus B square times A minus B equal to 0. Just double check it, that order is proper. Don't write it as A minus B times A square plus B square. This we do not write here because it does not follow from here. So now this is, let's check, it is A squared A minus B plus B squared A minus B is 0. Now let's call it P and let's call it Q. So PQ equal to 0. P is the matrix A square plus B square. Q is the matrix A minus B. So we have got two matrices whose product both are squared, so of course same size, whose product is 0. means product of P and Q is 0. So the product of two matrices is 0. And then one of them, remember A is not B. A and B are given to be different matrices. So A is not B. That means that this Q is not 0. So we are back to our result that product of two matrices is 0 and one of them, namely Q, is non-zero. Then the other, namely P, must be singular. Means you are saying that if this is the case, then other must be singular, means det of P must be 0, singular. And so det of A square plus B square equals 0. So we have finished this problem, that this kind of thing will come. Let us again do one definition, that is important one, of orthogonal matrix. Orthogonal matrix. So again we define that a square matrix A. So a square matrix A is orthogonal. So this is orthogonal if A transpose A equals I. So we have defined orthogonality as that is orthogonal if A transpose A equals I. A transpose, usually you know the transpose of A. That is, you change rows to columns and columns to rows. And of course we know that A transpose A equal to I. This implies now A transpose equal to I. Remember we did that AB equal to I implies BA equal to I. So I need not write. So A transpose is I enough for definition. And then we can have one result from it, important result. That first result is that determinant of orthogonal matrix, determinant of an orthogonal matrix is 1 or minus 1. I just have to start with the definition for the proof. A transpose A equal to I. So det of A transpose A is det of I. So det of I equal to 1. This is det of A transpose times det of A equal to 1. But we know that det of A is det of A transpose, because once you change rows to columns, it does not matter for determinant value. So determinant of A transpose is det of A. So det of A square equal to 1. This is A transpose. So det of A equals 1 or det of A equals -1. Means an orthogonal matrix can have only two values for its determinant, 1 or -1. Now we can also prove that product of two orthogonal matrices, is itself orthogonal. Straightforward proof. So a straightforward proof goes that let A and B be orthogonal, that is A transpose A be orthogonal. Orthogonal means A transpose A equal to I and B transpose B equal to I. Now you want to prove AB is orthogonal, product is orthogonal. So you want to prove AB transpose times AB. This want to prove I. There is question mark because still we have not done. We'll do it now. So consider AB transpose times AB. That is AB transpose. So we can play it like B transpose A transpose, which is called reversal law for transposers, which is called reversal law for transposers. So B transpose A transpose, that is AB now. A transpose A is I, so I can combine B transpose A transpose A times B. So you got B transpose I times B. You got B transpose B, and that's again I. So you get AB transpose is AB. AB transpose AB is I, and so you can say that AB is orthogonal. So if A is orthogonal and B is orthogonal, then AB also is orthogonal. Let me now solve and find out the form of 2 by 2 orthogonal matrices, which is very useful in application. Orthogonal matrices, 2 by 2 orthogonal matrices, general form. Means we want the matrices A, again A B C D, such that we want A transpose A equals I. So we want to solve for all A 2 by 2 ortho matrices. We'll prove that they're of certain form. So now we can write them as A B C D. So A transpose A will be, so A transpose, so I can write AC and BD and times ABCD, A transpose. So that will come out to be, so this is A square n plus C square. You will get A square plus C square. Then we'll again get AB plus CD. And again here we'll get AB plus CD. And we are getting B square plus D square. So this number we want, and this expression we want to be I, that is 1 1 0 0. We have already done some examples of this kind. So you want to now solve for ABCD such that A square plus C square equal to 1, AB plus CD equals 0, it's basically same, and B square plus G square equal to 1. Now because AC are real numbers and this is equal to 1, so I can take A equal to cos theta, B equal to sine theta, or negative sine theta. Similar, C equal to this one. Similarly, I can take B equal to cos phi and D equal to sine phi or negative sine phi. But then we have to also satisfy A plus CD is 0. That is cos theta cos phi and plus CD. That is, we can take just positive. Suppose sine theta sine phi is 0. So this is cos of theta minus phi is 0. Similarly, you can consider other case. And we find that in all the cases, we find that we can have 4 varieties of it, but out of them we will find that only 2 matters much. So ultimately we'll find that we have got cos theta and cos theta, negative sine theta, or one has cos theta, negative cos theta, sine theta, sine theta. Means that 2 by 2 orthogonal matrix, any 2 by 2 orthogonal has to be of this form, either this form or this form. Please note that the det of this det is 1, and if you calculate this det is negative of 1. That's all right. Orthogonal matrices have got determinant both, like either some of them have 1, so and some of them negative 1. So we got this kind of thing. So we can say that every orthogonal matrix is one of the 2 forms. So either diagonal on cos theta, off diagonal negative sine theta, or cos minus cos and sine theta here. So this fact we use very much. Now let me use this one in one problem. Notice first that A transpose A equal to I means that I can say that A transpose is the inverse of A. In general, inverse you have to find, but then here if A is orthogonal, then its inverse is just the transpose. It's just its transpose. No calculation, just transpose. Based on this, we can do one problem. So it is by definition. Based on them, suppose matrix A is given to be 1 2 2 2 1 negative 2 negative 2 2 minus 1, this one. Then you want to find that A inverse. Every matrix will have unique inverse as long as det of A is not 0. We can check that det of A is not 0. We want to find A inverse. Now note that for this matrix, if you write a matrix B equal to 1/3 of A, that is 1/3 of A, that is 1 2 2 2 1 negative 2 negative 2 2 negative 1, this one. Then this matrix B, A is not orthogonal, but B is orthogonal. Something derived from A is orthogonal. 1/3 of A is orthogonal. So 1/3 of A is orthogonal. We can check it quite easily orthogonal. So instead of multiplying, I give you a method that suppose we have got a 3 by 3 matrix, which rows are R1, R2 and R3. Think of R1 as a triple of numbers. So R1 is a vector. This is 1, 2, 2. For example, here R2 is 2, 1, negative 2, and R3 is negative 2, 2, negative 1. So if you think of them as 3D vectors, three-dimensional vectors, then just calculate the norm of each, norm or modulus of each vector, each R1, R2, R3. So modulus of this is 3, because 4, 4, 8, 1, 9. This also is 3, and this also is 3. So all modulus are equal. So these are the rows such that if you interpret the rows as a three-dimensional vector, then you are saying that everything is modulus 3, 3, 3. Now sort of take the dot product. So if you take R1 and R2 dot, that is if you follow 1, 2, 2 and dot 2, 1, negative 2, what do you get? You get 2 plus 2 minus 4. Wow, that's 0. Similarly, if you consider R1 and R3, you are done with R1, R2, R1, R3. So it means you are considering 1, 2, 2 and dot negative 2, 2, negative 1. That is negative 2 plus 4 minus negative 2 is 0. And you can also remaining one R2, R3. So if you do R2, R3, R2, R3, you will again get 2, 1, minus 2, and then you will get dot R3, that is minus 2, 2, minus 1. So that number will be negative of 4, and plus 2 plus that again 0. It means what we have done, that we have found that each row, we can do one column also, I'm just preferring row. So it is, we have found that every row, for every row, the number, suppose every row a b c, the number a square plus b square plus c square is same. That's one. And then every row is orthogonal to every other row in 3D space. That justifies the name of orthogonality. So it means what you are saying, that all row vectors, let's call them row vectors. So two conditions: all row vectors are of equal magnitude, here 3, 3, 3, and the dot product of every two row vectors is 0. That is, the row vectors themselves are perpendicular or orthogonal. So the name says orthogonal matrices. So let's use this here. B is 1/3 of A, and this kind of thing, orthogonal. So what we'll write, that we can check this, it is 0. And so 1/3 of A is orthogonal. So we can write 1/3 of A into 1/3 of A transpose, this one. So 1/3 of A transpose, and that number equals I. We can write, in fact, this way also, the other thing also, but we want A transpose. So we can just write this 1/3 times A, and this is 1/3 times A transpose equal to I. And so we can write A times 1/9 times A transpose equal to I. That clearly tells you that you have got something like AB equal to I. Does not matter AB equal to by I or BA equal to I, both are equivalent. And so we will say that the number 1/9 A transpose, this one, this expression, this is the orthogonal, this is the inverse of the matrix given by A, 1/9 A transpose. So A inverse will be 1/9 A transpose. So this is 1/9 and times A transpose, and then A was given to be this much, 1, 2, 2. So I can write A transpose as, I can just change rows to column. So this is 1/3 and times 1/9 times, this is 1, 2, 2, 2, 1, negative 2. We are changing rows to columns, transpose, negative 2, 2, and negative 1. And so that's my answer, that is A transpose. We can look at some other way also, but this is fair enough. Next, we do one problem which makes use of symmetricity or antisymmetricity property. So a matrix A has been defined or by the setting I plus S times I minus S inverse, where S is a skew symmetric. S is skew symmetric, and we have to prove that prove that A is orthogonal. Prove that A is orthogonal. And first part, and second part is that A equal to I minus S inverse times I plus S. Let me just rewrite it. So that's time I plus S. So let me first prove this one, that how you prove A is orthogonal. That's a little calculation. So I can start like this, that A transpose A, let's form A transpose A, that is I plus S into I minus S inverse and transpose and A. Please look at it very carefully because we will have lots of applications. Now, this PQ transpose equals Q transpose P transpose. That's all right. So that will give me I minus S inverse transpose. Make good use of brackets. I plus S transpose and times A. That A was already given. So A, I will write I minus S inverse and I plus S. That's already is there. Now, I plus S transpose. So A plus B transpose gives you A transpose plus B transpose. And A inverse transpose is nothing but A transpose inverse. So we can write this. So first here we write I minus S transpose and inverse. We can interchange this one. Here I transpose plus S transpose. I minus S inverse. I plus S. Now I minus S transpose, again A plus B transpose. So I can write I and minus S transpose inverse. This is I S transpose. That's nothing but negative S. So this is because this is skew symmetric. So I minus S and I minus S inverse. So I will write I minus S inverse and this is I plus S. Then I minus S inverse, if you write I minus S inverse, then what you can write? This is I plus S inverse. This is I minus S inverse, and I plus S. And so that will give you, in the end, that will give you I. Let's do once again and review it. Then this is, we wrote A equal to I minus S inverse I plus S. We have to prove that it is like this. So I plus S I inverse transpose and I plus I minus S inverse I plus S. In fact, we have used here already I inverse, and then we got this kind of thing, and ultimately we got I. We can also here already we assumed that A equal to, second part we have assumed. So second part without assuming also we can do that. Second solution is like this. Let's form A transpose A. A transpose, now A is I plus S times I minus S inverse transpose times I times A. So I plus S, I minus S inverse. Now again, same thing that we did, we can change this one first, AB transpose. So I can write here I minus S inverse transpose and I plus S transpose, I plus S, I minus S inverse. Notice how we have changing the track. We are saying AB transpose is B transpose, A transpose. I applied this to I plus S, and I minus S inverse, these two numbers. That becomes this one. And then I'm applying again as previous example, A inverse transpose is A transpose inverse. So transpose of inverse is inverse of transpose. So that gives me here I minus S transpose inverse. This is I transpose plus S transpose, I plus S, I minus S inverse. Now this is again I transpose minus S transpose inverse. This is I. This is negative S because S transpose negative S, because S is skew symmetric, I minus S, and this is I plus S times I minus S inverse. Now I transpose is again I, negative X transpose, that is S, because S transpose is minus S. This is this way, like 1 I minus S, I plus S times I minus S inverse. Now I do something magical. So already I have proved that these two matrices I minus S, so anything I plus lambda A and I plus mu A, this kind of matrix, they will always commute. It does not depend on S being symmetric or skew symmetric. For any matrix, these two will commute, because we can write I plus, we have already proved it, I plus, just to recall, I plus lambda A, I plus mu A, that gives I plus mu A plus lambda mu A squared. And if you write I plus mu A times I plus lambda A, that will again give you I plus lambda A plus mu A plus lambda mu A squared. So you are finding that these two are indeed equal, and so we have proved that I plus lambda A times I plus mu A equals I plus mu A times I plus lambda A. So we are just choosing here lambda is 1, mu is negative 1. So I minus S and I plus S commute. So it just interchanged, and then we are good. I plus S inverse times here I plus S will come, times I minus S will come, and then inverse will come. Now it is this inverse that becomes I, and these two also give you I, so that gives I. So we have proved that this A and B, we have proved that if A is this much, A is this, skew symmetric, then A is orthogonal. And A is also I minus S inverse I plus S. That we can quickly prove that I minus S inverse, because that way we'll write this way, that we have, last time we assumed that. So we have to prove now that I plus S and times I minus S inverse, this one, that also equal to, we have to prove now this I minus S inverse times I plus S. So it's again same thing, A and B commute, and suppose B is invertible, suppose B is invertible, then we will know that A and B inverse also commute, and B is invertible. So it means you are saying that A and B commute. So we can simply write that AB equal to BA, this is commuting, and B is invertible. So B is invertible, then we can multiply B inverse. So we want to prove that AB inverse is B inverse A. That's fine. Let's multiply this by B inverse. Multiply this by B inverse on the right side. So we can write that AB B inverse, and again we can multiply B inverse from this side. So 2 B inverses, and that equals B. So let's put bracket, and this is B inverse times BA times B inverse. What we have done is that we have multiplied both sides, pre and post, by B inverse. So B inverse AB B inverse is this. This becomes B inverse A association. This is B inverse. This is B inverse B, and times A B inverse. And that gives you that B inverse A, and this is already I. So B inverse A is A B inverse. So we have proved that if A and B commute and B is invertible, then A commutes with B inverse also. So if matrix A commutes with a matrix B, then it also commutes with inverse if it exists. Now already we know that I plus S and I minus S commute, and I minus S is invertible as it is already used in the problem, and then we can say that this is invertible, and so I plus S will commute with I minus S inverse also, and that is precisely what he's trying to say. So that finishes the solution, and so we have done both parts, that this matrix given by A is orthogonal, and also A equal to I minus S inverse times I plus S. So let me now stop sharing this screen. So that's all for now. Let's connect tomorrow.